Hello. I should do the tradition. Hello, I'm David. I'm the coordinator of the Maths Learning Centre. I'm going to get off your screen so you can see my writing. But now you've seen my face, you know what I look like. And therefore when you see me you can say, David, you gave this awesome revision seminar for Sam in 2017. Okay, so this is a revision seminar for Statistical Analysis and Modelling, affectionately known as SAM. It's 2017, semester 2, and I've been asked to talk about a few different things that are in the course. Well, let's see what we're going to talk about. I do have a question that I want to ask someone. Whoever wrote stat proofs, what do you mean?
In the exams, you'll find that you have to prove like the expected value of the mean squared, whatever it's called.
Okay.
And there's like quite a few of them.
Okay, so just for those who couldn't hear that, in some of the past exams there's prove that the expected value of the mean square error is sigma squared and that sort of thing. Okay. How does everyone else feel about me talking about that? Okay, good. I might start there.
It's worth like, in the past exams, it's worth like at least a quarter of the marks.
Did you have a specific one? All right, I'll find one. Let's have a look, eh? Not 2015, because why? Okay. Cool. Documents. Aha. So, all right, I'll show you my screen. This is the 2014 exam, and it's got several of them. So I might just talk through them so that you can see my thought process and hopefully be able to copy the sorts of things I think when I do these things. So let's do some examples. 2014 exam, question 4. Okay, so consider the linear regression model y, which is yi is equal to beta naught plus beta 1 xi plus epsilon I, where beta naught and beta 1 and xi are constants, and epsilon I is distributed according to a normal distribution with mean 0 and standard deviation sigma independently for I being equal to 1 to n. All right, that's your classic regression model. Okay, write down expressions for the expected value of yi and the variance of yi. Okay, I'm going to switch over the document camera. Okay, so I'm thinking, just trying to make sure in my head I know what's going on here, that the concept is that we have some sort of object, maybe it's a person, maybe it's a house, maybe it's a petri dish, maybe it's a flamingo, who knows, some sort of thing, and we've written down about it an xi and a yi. And this is our supposed relationship with how the xi is calculated from the yi. Other way around, the yi is calculated from the xi. And so the concept is that that all of your objects that have the same value for xi are likely to have different yi's, and the reason they're different is because of this epsilon I, because it's a random variable. And so this epsilon I is what causes the y's to be random. Yep. So the thing that causes the y's to be different is firstly that the object has a different x, and secondly that there's a bit of random variation. Okay. Cool. So when it asks us to find the expected value of yi, well, that's the expected value of beta naught plus beta 1 xi plus epsilon I. And expected values are able to be distributed over plus, and the expected value of a constant is still a constant. So I'm going to do this in 2 steps, even though in your exam you would normally write it down in 1 step. Like that. So beta naught plus beta 1 xi, that's a constant. I don't know what beta naught and beta 1 are, but they're constants. And the xi is constant too. I'm imagining that they're not chosen randomly. Well, I don't care whether they're chosen randomly, so I consider them to be constants. And so this is just this. Since they're constant, they're always the same, and the expected value of the epsilons is 0. The exam writer said write down, so you don't have to show working for this. You are allowed to go straight to there. Okay? And the variance of yi is the variance of this. And the rules for variances is that constants added on don't affect the variance. And so this is the same as just the variance of epsilon I, which is sigma squared. So the lecturer in 2014 expected the students to just know that that's what those answers were. I have derived them from what I know about how expected values and variances work. Okay, let's have a look at what part B is. Stupid touch screen. Consider the least... Oh, yeah. I searched through the exam for the word show, because that would tell me that there was a proof. I searched for prove first and didn't have it, so show was what I was looking for. Consider the least squares estimate of the slope parameter, which is beta 1 hat, which is equal to sxy divided by sxx, where sxy is that sum and sxx is that sum. Show that sxy is that. You may use the fact that the sum from 1 to n of xi minus x bar is equal to 0 without proof. Okay, that's a hint that that's going to be useful along the way. So I'm just going to write that down. I would really should have done this on dual display.
Do you want a version of it?
Bloody hell. Yep. Yeah, that'd be great. But you see, we can put it on the big screen for you guys. Okay. That's our question there. So we have Sxy is defined to be xi minus x bar, yi minus y bar, I equals 1 to n. And somewhere along the road, I am supposed to achieve this. Xi minus x bar yi. I need to hold that in my mind. That's where I'm going. Okay, so let me just pop this down the bottom of the page and hope that I have enough space to get there. Well, it seems to me that the difference between these two things is this minus y bar. So, my first instinct to do anything with this is to expand things out, because, you know, if I can't think of anything, expanding out brackets is not the worst plan usually. But it seems to me that I shouldn't expand out xi minus x bar because it's still here at the end. So I reckon what I'm going to do is this. Like that. So this thing gets multiplied by both of those. Okay, and then the rules of sum say that I can do these two pieces separately. Like that. And this is the thing I want. So I'm hoping that this is 0. So okay. Well, that y bar doesn't involve an I. And so it's the same in this sum. This y bar is the same for every I. So it's essentially the same as multiplying a whole lot of things added together with a y bar, which means I can factorize it out. Like that. Since it doesn't involve an I, it counts as a constant for this summation, as opposed to counting as a constant in terms of random variables, which it isn't. And I was told that I was allowed to say that the sum from 1 to n of xi minus x bar is 0 without having to prove it. And so I'm going to use that fact now. Which is kind of cool. I like that fact. If you add up the distances between all of the numbers and their mean, then including whether they're above or below the mean, it adds up to 0. That's what the mean is for. Okay, so that was part B. That worked remarkably well. But if I had expanded it all out, like xi, yi, x bar, yi, I would have made more work for myself. So I left that together because it was together at the end. All right, C. Whoa. Oh, that was just part I of B. I don't do blank pages in this exam. Okay. So part 2 is that hence express beta 1 hat in the form beta 1 hat is equal to the sum from 1 to n of ai, yi for some constants a1 up to an. Okay. Well, let me write down what beta hat actually is. Just a second, I know that. It's S, I think. Yep, got that right. Excellent. Okay. Okay. So the SXY we know is this, so I'll just sub that in. And the SXX, I don't feel like subbing anything in for that. And the reason I don't feel like that is that we were told right at the beginning the x is counted as constants. And so therefore the SXX counts as a constant too. So since it's a constant, I might as well just leave it as it is. Okay, so how about I bring that inside the sum, since I'm allowed to do that to things that don't involve I. Like that. I'm allowed to, if a whole sum of a whole lot of things is all divided by the same thing, I can bring it inside the sum. And, well, this thing here is a constant. So I'm done. I might as well just say, for the benefit of the person reading it, that note that xi minus x bar over sxx is a constant for each I. And so those are the a's that they're referring to. I could, if I wanted to, call them A, but I feel like that might be a waste of effort, because I'm just going to have to eventually put that back in, I'd say. Okay. Part 3. Show that the expected value of beta 1 hat is beta 1. You may use the fact that SXX is that without proof. Okay, sure. Let's see. So the expected value of beta 1 hat. Whoops. All right, well, we just figured out that beta 1 hat was equal to this thing that we just figured out. What was that? This. So that's the expected value of the sum from I equals 1 to n of xi minus x bar over sxx yi. Okay, so what I know about expected values are able to come in and out of some signs because they can be distribute over plus, and so I can do this. And xi minus x bar over sxx is a constant. It's not random variable. And so constants with regard to random variables can come out of expected values. And didn't we figure out earlier what the expected value of yi was? Yep, here it is. It's beta 0 plus beta 1 xi. Okay. Well, let's just think about where we were headed. We had to get to just beta 1 all by itself. So this is the bit that has the beta 1. I really need to try and make the beta 0 go away. So I might just expand that out so that the beta 0 and the beta 1 are separate from each other. Like that. Okay. So let's deal with this sum. I might be able to do something all in one go if I like. I know I can add these two things separately because that's how sum notation works. And I know that anything that doesn't involve an I can come out of the sum. So this beta naught and this SXX can come out. So I've got beta naught on SXX, the sum from I equals 1 to n of xi minus x bar, plus, now this beta 1 is a constant, and then, like it's actually a real proper constant, and so is this SXX, so I've got that beta 1 over SXX is 1 to n of xi minus x bar times xi. Okay. Now what have we got? The sum of xi minus x bar is 0. We used that fact earlier. And didn't they just tell us we were allowed to use the fact that SXX is equal to xi minus x, the sum of xi minus x bar times xi? And that's what I've got here. So that thing is SXX. And so that's 0. And the SXX is, I've divided by it and I've multiplied by it, so it's not really there. And so I get beta 1. Ta-da! So doing this proof was sort of a tension between expanding things out and avoiding expanding things out. Okay, so don't expand things out too far. If it's the only thing you can think to do, expand it out a little bit and then see what happens. And hope that something that you recognize is already there in order to use it. Okay. One last bit of this. So, show that the variance of beta 1 hat is sigma squared on SXX. Okay. My first instinct is to use properties of variances rather than the definition of the variance. So this would be the variance of that. So, all right, how do variances interact with plus? If you just got two things added together, it sort of behaves like expanding out a square, and so you end up with the variance of each bit and then like a 2 of the covariance. But if they're independent, you don't have to worry about the covariance bit. Okay, so since they're independent, I'm allowed to say bring the inside the sum. Since the yi's are independent. And I know the yi's are independent because the epsilon i's are independent. Oh, crap. Don't write that down yet, because I forgot to put variance in. All right. Now, let's see. Variance of, I can ignore the sum for a minute now. The variance of constant times function, the constant can come out, but it gets squared, because the variance is a squared operation, and so I get oh crap, there's still a sum sign. Okay. All right, now the variance of yi is sigma squared. We figured that out earlier, so we get like that. Okay. Well, I guess the things that don't involve I can come out the front. That's the only thing I can think to do at the moment. And the sum of xi minus x bar squared is exactly the definition of sxx. This is a squared, sorry, because I had a squared there. And so that cancels with that, and I get sigma squared over sxx, which was indeed the goal. Excellent. Right. Let's just see if there's any more. So, what morals can we learn from this story about doing these sorts of proofs? Sorry? Pull out the sums. Yeah, I did that multiple times, didn't I? All right, that's good. Let's write some of these down, eh? What else? Yeah, expand out, but keep things together if you want them to be together. Anything else? I noticed one which was notice when you have something you've seen before. So this thing here was sxx, and this thing here was sxx. So keep an eye out for things you've seen before. Okay, that'll do for that. I have a feeling that most of the proofy ones are involving things with sums in them, probably. Yeah, so that's probably most of the morals that I could give about doing those sorts of proofs. If you do future mathematical sciences statistics courses, you will learn some other morals about proving things that are involve multiplying by 1 creatively and adding 0 creatively, and noticing the sum of the probabilities of a distribution, which is just being 1. So really it's all about keeping an eye out for things that you've seen before, but there's one more strategy which is quite common in statistics proof, which is to unexpand. So don't make it simpler, make it more complicated temporarily in order to get what you want. So anyway, so that's both what expanding is. Okay, well, that's good. Let me chat a bit about what's this thing about normalization to a Z statistic about? Who wrote that and what do you want to know about it? Yep.
Basically just taking a normal distribution and standardizing it to the standard Z statistic.
Yep, and various uses for that?
Yeah.
Okay. I'll talk about that. And then maybe I'll do ANOVA. Okay, so I'm just going to title this normal distributions. And I'll include that under this heading, if that's okay. And before I go any further, I'm just going to have a quick look through your lecture notes. and then there's just random probability distributions. Okay, so I have some things that I might talk about if I were talking about normal distributions, and I don't know if your lecturer did any of them in any of the exams or assignment questions, so tell me if it looks a bit bizarre, but it's not the worst thing to talk through. Okay, so in this course you only learn the names of two distributions. You learn the name of the normal distribution, which is a continuous distribution that has a certain shape, and you learn the name of the binomial distribution, which is a discrete distribution. But you don't learn the names of any other distributions as far as I know. There are many. Well, actually you do. You learn the name of the t distribution and the f distribution as well. You didn't notice that at the time, but they are distributions that you learn the names of. But there are many, many distributions that have names, like the Poisson distribution and the Erlang distribution and the log normal distribution and the chi-squared distribution and any number of them. And then there's zillions of distributions with no names. They're just there. The concept is that for anything that you could possibly record or write down or measure, somewhere in the universe there's a list of all of the things it could be and how likely they all are. I imagine an angel sitting there with a big book. Say, oh no, they're measuring people's heights. Pull out the distribution and tells you what all the numbers are. So that's my big head. The other thing I imagine is that all the distributions live in this city, and you can look up where they are. And so when you ask RStudio to look up the probabilities in a distribution, it's actually looking up the street directory and like the Google Maps for the distribution city and finding which street everything lives on. And so when you talk about the degrees of freedom of something, that's really the address. It's the distribution finder, DF, which is the address which tells you where to look for things. Okay, so normal distributions have two pieces of information in their address. They're not called degrees of freedom, but they're called parameters. And the normal distributions tend to have this sort of shape. It's supposed to be symmetrical on either side. Us humans are not particularly good at drawing them by hand. I'm sure that if with a great deal of practice you could, but this is good enough. And they have a mean somewhere in the middle and a standard deviation which tells you how wide it is. And for those of you who are interested in the shape of this function itself, the standard deviation is the distance between the mean and the inflection point just here. It stops going round and down and starts going down and out at that point. So, kind of cool. And the formula for this height involves the exponential function. And let's see if I can remember it off the top of my head. It's got an e to the minus x squared in it, and it's an x minus mu over sigma, and I think there's a half here, and there's like a 1 over root 2 pi sigma, I think. I'll just look it up. No, you don't need to remember that, but I just think it's fun to remember it. The lecture notes are already there, but it won't be recorded unless I put it on the other screen. So, yep, I was right. Woohoo! Excellent. I like it when I can remember things. Doesn't happen very often. Okay. So I don't think you're expected to remember that. And the reason is that you could, if you wanted to, calculate areas under this curve which would represent probabilities, but it's impossible to integrate this function. Okay, the only way to integrate this function is to approximate the integral. There is no formula for the integral of this function, which bugs statisticians no end, but it's just the way it is. See, it's because of this x squared here. If I was going to integrate it, I'd have to use substitution, and then I'd need an x down here, but it's not there, so damn it. Okay. All right, so that's the normal distribution, and there's one for every mean and every standard deviation that you could possibly think of, except the standard deviations have to be positive. So this is the mean. So in the Google map for Normalville, where all the normal distributions live, there's all these ones with mean 0 that have different standard deviations. Sort of really, damn it. You know, there's this one, and there's one that's sort of skinnier, there's one that's even skinnier, there's one that's flatter, one that's really flat, and so on. In order to maintain a total area of 1, which is, it has to represent a probability, they get shorter as well as wider, like that. And so these ones all have a mean of 0 and different standard deviations. And then there's ones, of course there's infinitely many, like it's a real number, but then there's ones with a mean of 1, which are all a little bit further over. And then there's ones with mean of -1. Skinny, not so skinny. The pictures get worse the further out I go. Okay, and so there's this big cloud of them, right? The standard deviations go all the way up to, I mean, there's 0 at the top and infinity down the bottom. And so, right, and right in the middle, there's this one, which has mean of 0 and standard deviation of 1. That's called the standard normal distribution. And we label it with the letter Z for no reason that I'm aware of. It's probably like a German word or something. Okay, so the labels go like this. This is like the normal distribution with mean 1 and standard deviation 1, and this might be the normal distribution with mean 1 and standard deviation 1/2, and this might be the normal distribution with mean 1 and standard deviation 1.5, normal distribution with mean 1 and standard deviation 2. This is the normal distribution with mean 1 and standard deviation 1, mean 0, and okay, and there's infinitely many of them. Etc. Okay, and this one in the middle is also called Z. And you'll notice that the letter Z, if you turn it this way, is an N for normal. It's not a very good reason, but it makes me happy. Okay. And why do we care so much about this N, this Z, this standard normal distribution? We care about it so much because of the properties of how expected values and variances of random variables work. So it turns out that if you have a normal distribution with any particular mean or any particular standard deviation, you can convert it into a normal distribution with mean 0 and standard deviation 1. So if x is distributed according to a normal distribution with mean mu and standard deviation sigma, it's possible calculation on x to get the answer to be distributed according to this. And so that standard normal distribution turns out to be the only one we need to know, because I can figure out all the other ones from there. And in fact, when R calculates normal distributions, it converts to that one and then converts it back to yours. So that's what it does. I could be wrong about that. It could be just using a fabulous Taylor series for the integral of e to the minus x squared or something. It's probably what it's really doing. I don't know. But I imagine that that's what it does. It turns it into a standard normal distribution. And so the way it works is this. If I take any random variable and I subtract a constant from it, then what will happen is you'll subtract that constant from the mean. And so if I go x minus mu, that will be a normal distribution with mean 0. So if I subtract a constant from something, it changes the mean, but it doesn't have any effect on the standard deviation. That's how variances and standard deviations work. And so I can subtract the mean, and then I'll have something with mean 0. And then if I divide it by sigma, when you divide by a number, it divides the mean and the standard deviation by that number. So if I divided by 2, I would get the mean would still be 0, because 0 divided by 2 is 2, and the standard deviation would be sigma on 2. And if I divided by half, the mean would be still 0, because 0 divided by half is 0, and the standard deviation would be 2 sigma. And if I divide by sigma, the mean will be divided by sigma, and it'll still be 0, and the standard deviation will divide by sigma, and it will become a 1. So it turns out that if I subtract the mean and divide by the standard deviation, I get a standard normal distribution. Fabulous. That's my GPS, right? That in Normalville, my GPS says how to get from standard normal station to all the other addresses in Normalville. All right? Or actually more the other way around. It tells me how to get from X back to Z. It does work the other way. If I have a standard normal distribution and I want to create a distribution with a certain mean and a certain standard deviation, just as an aside, also if X is a normal distribution with mean mu and standard deviation sigma, then you are guaranteed that X is going to be the same as calculating sigma times Z plus the mean. That's just rearranging this formula. But that tells you how to get from the normal distribution to any normal distribution you would care to, you would desire to make. Okay, why do we care? Because our machines that we have programmed using this information can now tell us probabilities involving distribution at all. We don't have to do this. Back in the day, before computers could do any normal distribution, they just had a table that told you all the probabilities, well, for every 2 decimal places of the standard normal. And if you wanted to calculate normal distribution probabilities, you'd have to convert yours to normal and look up the standard table and then convert it. So you used to have to do that. These days you don't have to, because the computer does all that for you. However, it is useful in situations where you don't know what the standard deviation or the mean is. So let me just show you something. Suppose X is a normally distributed variable with mean, 10, and such that the probability that X is greater than or equal to, 15 is 2%. What is the variance of X? This is something that we can do. Here we go. So here's some problem solving for you. So my first step in my problem solving, because I always do this for all problems of any kind, is to draw a picture. So this is my X. It's got a mean of 10 and a standard deviation of, well, I don't know what that is. All right, I might even call it sigma until I know what it is. The standard deviation of X. Right. So there's my diagram. And I know that if I put 15 here, that this area is 0.02. Because that's the information I've been told with this probability here. Okay. Now, I can't do the inverse normal distribution. I can't do like norm-inv if I don't know what the standard deviation is. So R is not going to tell me the answer. If I knew what the standard deviation was, I could take this 15 and it could tell me that that was 0.02. And I could take the 0.02 and it could tell me what the 15 was. If I use like norm, d-norm and p-norm, that's what they're called in R, isn't it? Q-norm. Oh crap, anyway. One of them. No, d is the height. Yes, d is the height, p is the probability, q is sprite. So I could use p, if I knew what the standard deviation was, if I knew what this was, I could use p-norm to figure out the 0.002. And if I knew what standard deviation was, I could use q-norm to take the 0.02 and figure out what the 15 is. But I don't have any way of getting R to tell me what the sigma is. But that's okay. I just need to make a new random variable whose standard deviation has one that I know. So why don't I write Z is equal to x minus the mean divided by the standard deviation. And that random variable has mean 0 and standard deviation 1. So 15 minus 10 would be 5, so this would be 5 divided by sigma, just there. And this probability is still going to be 0.02 because every x corresponds to exactly one z, and so the x's that are beyond 15 correspond exactly to the z's that are beyond 5 on sigma, and so the probabilities will still be the same. Okay. But I can do the formal working for this as well, which I'm going to put down here. The probability that x is greater than or equal to 15 is the same as the probability that x minus 10 is greater than or equal to 5. That's subtracting the 10, which is the same as the probability that x minus 10 over sigma is greater than or equal to 5 on sigma, which is the same as the probability that z is greater than or equal to 5 on sigma, because that's what z is. And I know that this probability is 0.02. And so now I can use R or other piece of useful information to tell me what that 5 on sigma has to be in order to make it work. So this would be, just let me, okay. So in order to use the Q-norm function in R, I would need to use this probability here instead, because it only gives me the left-hand probability. Which means that the probability that z is less than 5 on sigma is 0.98. And so I can do Q norm (0.98), a mean of 0 and standard deviation of 1. I believe if you leave off the 0 and 1, R assumes that it is 0, 1 if you don't put them in. So you can just do that. All right, and that's what the 5 on sigma will be. I wish I knew that one off the top of my head. And I'm just looking it up on Wolfram Alpha, because this computer doesn't have R. There we go. .054. So 5 on sigma is 2.054, and therefore my sigma go up there would be, will be equal to whatever that is. Come on, 2.4. 2.434. And I was asked for the variance, which would be sigma squared, so that would be that squared. Which should be, I don't know, 5.92. Okay, damn it. So that's one way of using the standardizing to normal to useful effect. In an exam, if your lecturer wanted you to do that, they would give you a selection of different Q norm calculations and you would pick the one that matched what you were trying to achieve. So that's why it might be useful to do that. I would love to give people an assignment with a broken RStudio that could only produce the standard normal and ask them to do probabilities for ordinary normals and see, and that'd be a great small group discovery. Maybe not. I don't know. Sounds like more fun than what they normally give people. Okay, so that's pretty much it with normal distributions. The only other thing to know about normal distributions is the same with other distributions. If you want any probabilities, your computer will only tell you probabilities to the left. So you have to construct them out of those pieces. And you're allowed to use the fact that it's symmetrical. So this is not about the converting, but just saying, you know, mean 6 and standard deviation 2, find the probability that x is between, I don't know, 5 and 8, capital X, something like that. Then there's 6, there's 2, and we're going from 5 to 8. And the area is the probability I want, but my computer is only going to tell me left-hand areas, so I have to construct this area out of plussing and minusing left-hand bits. So I could do this bit minus this bit, because I'm only allowed to use left-hand bits. So that would be equal to the probability that x is less than or equal to 8, which is the green bit, minus the probability that x is less than or equal to 5, which is technically strictly less than 5. Not that it makes any difference for a normal distribution. So less than or probability of less than or equal to is the same as probability of strictly less than for a normal distribution, because you can go all the way up to 4.999999999. And so it doesn't make any difference to the area. Binomial distributions less than and less than or equal to are different because you can't have the non-whole numbers in between. So, right. Cool. Everything has to be constructed out of that. There are multiple ways of doing that. If you happen to have a normal distribution table that you held in your hands and that was the only way of calculating normal distributions, and that normal distribution table only gave you outside areas, you would have to construct in a different way. So if you have a book with a table in it, most of them only give top-end areas, And so the only way to do it is to go, well, I'm going to have everything, take off that top end, take off the top end for 7, because that's the same as the bottom end for 5, and that should be the correct area. So you have it easy with probability distribution calculations. The poor people over in economics have to do it from a table. Even though their computer can calculate it, they're taught to do it from a table. I would like to say they're taught to do it to table because it's lots of fun to do that sort of problem solving, but that's not why. Anyway. Okay, so cool. Does that sort of cover what you wanted to know? Good. ANOVA. What do we want to know about ANOVA? It's written pretty big. Is that just because does that mean that it's like really looms large in your mind, or is that just a coincidence? It's like when we did the Maths 1B revision seminar and they wrote limits, right? That was you, wasn't it? So is that the same principle, or who knows? Did you write? Who wrote that? Yeah. Okay. So, all right, I can talk a lot about ANOVA if you want me to. I'm not entirely sure what the best things to say are, but I can start. So I might just sort of locate ANOVA in the grand scheme of hypothesis tests first. So we have all these different hypothesis tests procedures, and they're designed to answer different kinds of questions with different kinds of data. And the kind of question you're asking and the kind of data you have dictates the sort of statistics you have to do. So that's basically it. So ANOVA goes with this situation. You have objects which may be people or boxes or petri dishes or moments in time or whatever it is that they are. These are your subjects. And to a statistician, there are no people or chickens or flamingos or petri dishes or houses. There are merely sources of variables. Okay? So, you know, there's just sources of variables, and there they are, and they produce this lovely CSV file that has all these numbers in it. Okay? Or words. That's all there is. And your source of variables today, which is what a subject is, produces one variable, which is a category. You call it categorical variable in this course, do you? Did you do variables? Did you do types of variables at the beginning of this course?
We did discrete.
Oh, damn it. That's okay. So it's discrete, but it's not a number. It's a category. Okay. Serious failing. And it comes in at least 3 categories. So perhaps it's 3 different types of treatment. So placebo, no treatment, and the actual drug, for example. Or perhaps it's 3 different breeds of chicken, you know, a black Australorp, Rhode Island Red, and can't think of another one off the top of my head, but that's pretty good to have 2 breeds of chicken in my head. It could be anything that allows you to split your subjects into separate categories. Okay? And then the other variable that you've written down is a number. I'm going to draw number as a scale on which the number is recorded. This is like your x-axis or your y-axis or whatever it is. Okay, this is the situation in which ANOVA is used. You have 2 variables recorded on each individual, and your data would normally look like this. So subject number 1, maybe they're in category A and they have this number. Subject number 2, they're in category A as well and they have this number. Subject number 3, they're in category B and they have this number. And so on, right? R is clever enough to, if you don't have all, you could have another A further down, you don't have to have them one after the other for R to be able to do its job. It's clever enough to have them mixed together. Microsoft Excel, on the other hand, prefers them to have them in order. So that's why R is better. Not to mention being free and having ggplot2. Okay, so that's what your data looks like. It's always helpful with statistical things, especially hypothesis testing, to imagine what your data looks like, because that helps you figure out, firstly, what bit goes where in the code, in the R code, but also helps you figure out what the variables are. Because I have written down a category for each person, it counts as a variable. It's a discrete variable, because it only has certain things, but it's not even a number. So this is the situation we're in. And what we're interested in is which category you're in. Does it make a difference to the number? Does the category that you're in make a difference to the number that you have? So for example, does the breed of chicken make a difference to how many eggs it lays in its lifetime? Does the treatment that you give your subjects make a difference to their weight loss over the course of the study? Does which school a student comes from, well, make a difference to their grade? I would hope not. Except for some of the really posh schools, and I hope they get really worse. I hate when people assume that I know what their school is just from like an abbreviation. Go PAC, and I go, I don't know what that means, because I'm not from Adelaide. And even if I was, I would refuse to know what that meant. Now, I don't really care about your school, but that's the point. I don't care, so don't tell me. I actually, when I was a student, I loved telling people, when people asked me, what school do you go to, because it's such an Adelaide thing to ask. And what school did you go to? Broken Hill High School. And they'd go, right. And they wouldn't have a thing to say, so that was good. I'd have to find something more interesting to talk about, like what sorts of things do you like to do when you're not at university? What are you talking about? I'm at university all the time. Anyway. Not that they had Hub Central in those days. You couldn't be here 24 hours a day. Not without getting wet, anyway. And you can see I've already been talking for an hour and a half and I'm losing my mind. So where are we up to? ANOVA. That's what ANOVA is for, okay? It's designed for this situation. Now, the way that we figure out how to use statistics to answer this question is via means and variances. Okay? So our way of deciding whether the category makes a difference to the number is to imagine all of the individuals in each category as belonging to a different distribution, each with a mean of its own. And we ask ourselves, are all the means equal to each other? Or are they not all the same? That's how we imagine ANOVA to work. So we say something like, well, we imagine each category's numbers follow their own distribution, each with its own mean. And we go, mu A and mu B and mu C and however many of them there are. And that's how we imagine it. And we turn our question of, does which category you're in make a difference to the number? We turn that question into, well, if the category made a difference to the number, then those means would be different. Or at least they wouldn't all be the same anyway. So our question becomes, are all the means equal or not? And if they're not, then the category does make a difference. Not to say that it causes, statistics never tells you that anything causes anything. That's not what statistics is for. That's what experimental design is for. Statistics just tells you that some things are numbers are related to other numbers. Okay? So it doesn't tell you that the category causes the numbers to be different. It just says that when the categories are different, the numbers tend to be different. Okay. So are all the means equal? That's my new question. And so I can turn that into a hypothesis test, because now I can say that my null hypothesis is in fact that they are all equal. And my alternative is this how you do it in this course, null and alternative? And my alternative hypothesis is that they are not all equal, because it's too hard to say it every other way. So it could be, the alternative is, it could be that mu A is the same as mu B, but mu C is different. It could be that mu A is different and mu B and mu C are the same. It could be that mu B is different and mu A and mu C are the same, or it could be that they're all different. Any one of those is okay to me, because that would mean that the category makes a difference. All right, so I go, well, are they all equal? And then the way to do hypothesis tests is I need to somehow turn all of my data into a single number that represents how far away from the null hypothesis I am. Okay, all of my hypothesis tests are of that vein. I have to go, right, all my data has to become a single number that somehow represents my situation. And I'm going to ask myself, what are all of the, if the null hypothesis was true, what are all the possibilities for what that single number could be, and how likely they are, and mine, the one that I actually got today, how does it compare? That's what I'm going to ask. So I need to turn all of my data, all that data I drew before, all my data has to become a test statistic in such a way, and this, in ANOVA it's called F after Fisher, who invented ANOVA, test statistic in such a way that I know what this distribution is if the null hypothesis is true. Now, there are other ways of doing this, but the ANOVA is the most powerful one that we have, and, you know, it's been pretty popular, and so people know about it, and so you need to know about it too. That's my goal. Now, the process by which it produces this test statistic, in our case, is because that we're interested in means. The process by which we produce that test statistic is going to be via variances. And so this process that does this is called ANOVA, which stands for Analysis of Variances. Okay, so what Fisher did is he imagined it this way. He imagined it like this. This is my category, A, B, and C. And these are all of the values for my number that the people in A could possibly produce, or flamingos or petri dishes or whatever it is that they are. And these are the ones for B, and maybe these are the ones for C. Okay. So you're probably used to seeing this as a set of box plots. This is a jittered scatter plot, which is better than a box plot, because box plots are stupid. Not to say I have anything against Tukey and his box plots. They're very pretty, but I like to see where all the data is. And the box plots only have 5 bits of data for each one. So that's just my opinion. Okay, so this is where all my data is, and in fact this is my imagining of where all the data could be. These are my distributions. And my question is, if the means, this one is, it's seeming to indicate to me that the means are different. So the mean for A is going to be about here, and the mean for C is going to be here, B is going to be here, and the mean for C is going to be here. And I'm looking at them and going, well, those means look different to me. And what I would like is some number to indicate how far apart they are. And so what I'm thinking is that even if those means were this different, if the spread was really wide for each of them, it would be very difficult to tell which group I was in if I just mashed everyone together. So if I put all these on top of each other, right, and I didn't know where the labels were, it would be almost impossible to tell based on your number whether you were in group B or group C. But if you had a really high number, I'd know you were in group A because all the group A's are up here. So that's the thing. Can I tell just from the number which group you're in? And it would depend on how spread out everything is. If everything's really spread out, there's not going to be really any way of knowing. And so I need to take into account the variation. And so what I'm going to do is I'm going to add up. Right. So I'm going to imagine how different any two individuals could be. And I'm going to say, can I tell that these two, if I pick two random individuals, can I tell how different they're going to be based on the fact that they're in different groups? Or not? So, there's going to be a grand mean if I put them all in one big group. Because if the null hypothesis is true, they really are one big group. So it's going to be down about here. That's my grand mean. And when you do this in R, do you do in like an LM, like a linear model? Okay. And I'm just going to look this up in your notes because I want to make sure that I'm matching with what your lecturer does. Okay, so you've seen right, I'm talking about one-way ANOVA here. What the frill? Right, I can't tell how she does it, so I'm just going to talk about it my way. Okay, so I'm going to do the total amount. So if indeed my null hypothesis is true, everything is just random variation around this grand mean. It doesn't look like it in this because the null hypothesis isn't true. But if it was true, everything's variation around this grand mean. And the total amount of variation, and so that's my model. My model is that the best is that each individual's number is the grand mean plus some error. So the model. Each person's number is the grand mean plus some error. Okay, no matter which group they're in. On the other hand, what we're comparing it to is this model. It'll be whatever mean for your group that you're in plus some error. That's what I'm interested in. And each person will have their own particular group, or object. And I want to compare these to each other. So the error in this model is how far you are from your group mean. And the error in this model is how far you are from the grand mean, which is the total amount of error. And so you have that thing here. So you add up how far everything is from the grand mean, and that's the total amount of variation. You add up how far everybody is from their group mean, and that's the variation in this model. And then the leftover variation is how far all the means are from their group mean, from the grand mean. But you include that once for every individual in the study. Yeah, and so you create this table, which goes the category and the residuals sum of square, the mean square, and your F and your p-value. That's what the table looks like. Though this last bit doesn't actually have anything at the bottom there. That's what the table will look like when you get a computer to calculate it. Different computer systems will put those columns in a different order. Most of them put the DF after the sum of squares, but R puts the DF first. Of course it does. So we're interested in these sum of squares because that's how we do error. You always add up squared differences because it makes my maths easier, believe it or not. Okay, so, and there's also a total here which isn't shown in the R's calculations. Okay, so the sum of the squares of everything from the grand mean, that's what goes here. And this sum of squares here is how far every group mean is from, yep. Let me just check that I've got that right. I almost always get this bit wrong. I know the important bit. Yep. Yes, your course has got more complicated ANOVA stuff in it than I have. Crony adjustment, analysis of variance. All right, and here we go. Yep, I've got it now. So between groups and within groups, and this is called often in Excel it's called the category and the residuals, but it's also called between and within. So between the groups, I'm going to add up how far everything is from its group mean, every group mean is from the grand mean, and I'm going to include that once for every individual. Y bar I minus Y bar squared. Okay. And then this one is going to be the sum of everything from its group mean. And this one is the sum of everything minus the grand mean. So that's all the amount of variation that's going on here. And I want to compare this variation to this variation. Because if there's more variation just everywhere, which is the residuals, then I won't be able to tell that the means are different. And so the degrees of freedom for each of these is how I take into account how much data there is. So there's only, in my case, there's only 3 groups. And so I would have 2 degrees of freedom here. Like this is the number of groups minus 1. Number of groups minus 1. And this is the number of individuals minus the number of groups. And this is the number of individuals minus 1. then to get the mean square, you go this divided by that. So SS stands for sum of squares. The SS in this row minus the degrees of, divided by the degrees of freedom in that row. SS for this row divided by the degrees of freedom in that row. And the F is these two things divided by each other. So the mean square, this says mean square here, for my between, divided by for the mean square for my within. And then you look up the p-value in the appropriate distribution. It's a lot of calculation to be done to get what you want, but it is a very, according to Fisher, it's a very effective way of combining all of your data in order to answer the question that you're trying to answer. So I don't know if your lecturer does it, but some other lecturers in other courses in the past have done things where they've left these ones blank, told you what these numbers were, and asked you to calculate the rest. So they'll give you what these numbers are, and they'll leave these ones blank because you figured them out from the situation. You say, oh, well, you've got 200 participants and 3 groups, so this one's 2 and this is 198. And then you do the divisions that you need to do and you calculate the F statistic from that. So it's a classic exam question that people give. And I might even find one. And let me find an exam question.
We had a similar question to that in one of our tutorials.
Mm-hmm. It's not coming up. Not in the 2014. Well, maybe it's not in exams traditionally. But as I say, there's only been like 3 or 4 years of exams at all. Linear regression. Ordinary regression. Multiple regression. That's it. I can't find one, but you say there was one in the tute. Yeah, okay. I don't have an example to hand at the moment, but that's the idea behind it. That's the idea of ANOVA, and you normally read everything off of the output from R. To look up the p-value, you need to look up the correct F distribution. And so you have that the F statistic has distribution F with that degrees of freedom. Has 2 numbers for its degrees of freedom, which is your address. So there's a different F distribution for every pair of degrees of freedom. And they all look like this. They're longer on one side than the other. And when you do the probability, you only do the top end because F distributions can only be positive because when you calculate them, everything's squared. So, yeah. In case you ever want to draw a picture of your probability distribution there. So in RStudio, you could go, F, the PF, just like there's a P norm and a PT and a P whatever. Yeah. Well, that's my imagining of how ANOVA goes. And I've lost the beginning of that one. However, it's worth mentioning that you use ANOVA in multiple places in your course because it's a flexible concept of trying to tell how far apart, how your model compares to no model at all, or even how it compares to some other model. And so it's just a warning. That was one-way ANOVA. Yeah. Is also used to help with regression. So anytime when you're trying to compare how far everything is from your model, ANOVA comes up. So when you do a regression, if this x variable didn't make a difference to what the y variable would be, then the best estimate you have for the y variable is just the mean. Like they're just the mean plus or minus a bit. And so you still have that grand mean. And so what you can do is you can do exactly the same thing that you did with the ANOVA just there to calculate how far away everything, how much variation there is if you take into account that there's a line of best fit. And so you can say, how far is everything from the grand mean? That's the total amount of variation. And then you can say, how far is everything from the regression line? That's the error, the residuals. And then you can say, well, how far is the regression line from the grand mean? That's the model. And so you can do the sum of squares for the model is for every element, how far is this from y hat? And the SS for the error is how far, no, wrong one. How far is y hat from the grand mean? That's the model. And the SS of the error is how far everything is from its y hat. So this is how far the line is from the grand mean. And this one is how far everything is from the line. And together, that's how far everything is from the grand mean. This is the SS total. And so what you do is you divide these by their appropriate degrees of freedom and then divide those two answers, and that gives you an F just like it does with ordinary ANOVA. And that's why every time you do a regression it produces an ANOVA table that gives you a p-value to say, does the model do anything? Yeah. But then you get separate regressions to tell you, you get separate statistics to tell you about each individual variable. Yeah. So I guess this has a degrees of freedom, which is the number of variables minus the number of parameters minus 1. And this is the number of the n number of individuals minus the number of parameters. And this is always the number of individuals minus 1. So that's why when you do a regression, your degrees of freedom is n minus 2. Because it's n minus the number of parameters. So when you do a regression, there's a beta 0 and a beta 1. There's 2 parameters. Yeah. Okay. So there you go. That just be aware that ANOVA is also used to do regression. And that comes up there too. All right. I'm nearing the end of the amount of energy I have for this and the amount of time. So there's a thing there that says linear regression. I guess I could talk about that for a few minutes, but it's going to be fairly general because I've got 10 minutes. Okay. I should say something that I didn't say about ANOVA before. Every statistical procedure with hypothesis testing comes with a batteries not included warning that says you have to check if various distributions and normal distributions in independence and stuff is correct before you put faith in your p-values. Yeah. So each one of them has a list of those conditions, or I think they're called assumptions in this course. And all of them are about, almost all of them are about the way the probabilities are arranged. So they're about the normal distribution, which is about how probabilities are arranged, or they're about independence, which is about how probabilities are arranged. So the reason you need those assumptions is because you're going to calculate a p-value, which is a probability. So unless you know how the original probabilities are arranged, you can't really tell how to calculate that final probability, which is why you need those assumptions. But later generations of statisticians, since these were created, have proved that you don't have to worry about a lot of them as much as you hoped, because as long as it's roughly okay, it'll work out, the probability will work out roughly okay as well. And no one uses p-values as a hard and fast, well, no one should use p-values as a hard and fast way of making decisions. You shouldn't go 0.49, yay! You should be, you shouldn't say 0.049 or 0.051, oh no. Everything's like, oh yeah, we've got a certain amount of evidence, that's telling me I should do more research in this, or not. Okay, so anyway, linear regression. The concept of linear regression is this, basically. You have a number recorded on every one of your little boxes, or sources of variables. And you're interested in how various other things affect the result. Not to say that they cause the result, you'll never know that without some very good experimental design, but to say that they help you calculate and predict what the number is. So I'm going to call this an outcome. Your lecturer probably calls it a response variable. Yep. It has different names in different faculties, so I need to try and match with yours. And these are explanatory variables. So explanatory variable number 1, which might be a number, an explanatory variable number 2, which could be a category, and I'm going to realise that in my computer as a 0 and a 1. An explanatory variable number 3 could be a number as well. And my idea is that I can calculate what the response variable is based on what all of those other variables are. So if you have my little box, my little subject, maybe it's a person today, and you tell me that x1 is 5 and x2 is category A and x3 is 17, then I want to know that I can use all of them to calculate that actually the response I expect is maybe, I don't know, 20.8 or something. Just making up random numbers here. Now that won't be exactly equal to whatever response they actually give, but the point is that you want to try and predict what their actual response is going to be as accurately as you can. Okay, and the way that you do that is via a linear function. And so we're going to say that the response, which is traditionally called y, is going to be some number plus something times whatever x1 is, plus something times whatever x2 is, plus something times whatever x3 is, and a bit. And for these things that are categories here, we're going to rationalize that one of them is 0 and the other one is 1 so that we can sub it into this formula. Did you do dummy variables? Should have if you've done an ANOVA as regression, but anyway. So if you have categories, you've got to give them numbers because this is a numerical formula. I can't put the letter A in this position here and have a reasonable answer. So I'm going to letter A, which is 0 as opposed to... Okay, so that's my response. And the idea is that I want to have some sort of linear equation that once I put the x1 and the x2 and the x3 in, if I ignore what the epsilon I is, it'll give me an estimate of what the yi is. The big problem is I don't know what these betas are supposed to be. My imagining is that there are some betas that the angel with his big book keeps to tell me what they really are, and I need to try and calculate the best estimates that I have for those. So in this case, it would be like a 3-space of best fit as opposed to a line of best fit. You just need to get as close as possible. And one way of doing it is to get your computer to try all the possible values of the betas and see which of them is the closest. But you need a way of measuring close, right? And that's what this SS thing that I just talked about before is. This SS error is my way of measuring closeness. So I'm going to get an estimate. Estimates for beta 0 and beta 1 and beta 2 and beta 3, which are going to be called beta 0 hat and beta 1 hat and beta 2 hat and beta 3 hat. And my estimate for yi will be yi hat. Beta 2 hat x2 plus beta 3 hat x3. And there won't be any error because I don't know what the error is, so I'm just doing the best I can. Okay. And the matrix algebra and calculus simultaneously tell me what these betas ought to be. Now, I'm just going to... I don't think, looking through your notes here, I don't think you've had any explicit instruction on how the matrices do that. No? Good. That's for a whole other course. I think that's in Statistical Modelling and Inference, the second year course. Yep. So what you imagine is that your entire list of data is a whole lot of lists of x1s, a whole list of x2s, a whole list of x3s, and a whole list of ys. You create a matrix out of the x's and of... You did do that? Ah, in the tutes, right. You make a matrix out of the x's and a matrix out of the y's, and you can reimagine this as a matrix multiplication. So I can reimagine, and this is why Fisher was so bloody clever. He imagined all of this as vectors. So you imagine that yi is, which was beta 0 plus beta 1 xi plus beta 2 x 1i. There's supposed to be i's on all of these, plus beta 3 x 3i plus epsilon I is created by a dot product. Like that. And then you go, well, that's just position 1 of the y vector, and position 2 of the y vector would be this, but with the second set of x's and the second epsilon I. And so you would get that's backwards from how matrices are normally labelled, I'm sorry. But then y2 would be made out of the second set and y3 would be made out of the third one. And so on, because that's how matrix multiplication works. And you get this thing. So you get a vector of y's is a matrix times a vector of betas plus a vector of epsilons. Yay. And then there's all these matrix multiplication things and transposes and inverses that allow you to calculate what the beta hats are. But I'm pretty sure that that's not a major part of your course because I haven't seen it in any of the exams. But this sort of thing is in the later maths degree and economics degree courses, that they do it all with matrix multiplication. And that's because when you want to find the shortest distance between one place and another, which is what we're trying to do, we want to minimize how far away my line of best fit is from the data, then what you need to do is an orthogonal projection. And so therefore orthogonal projection from Maths 1B does statistics for you. So there you go. Anyway, that's not a huge part of the course, but that's the one of the ideas behind it. And so you find ways of calculating what this vector of betas is. Yeah, but you know, anyway. You have formulas for calculating the beta when you have simple linear regression. If it's just yi is beta naught plus beta 1 xi, and there's only one variable, then you have formulas for how to calculate the beta naught and the beta 1 that you know, that you've been given. But if you're in multiple regression, you haven't been given those formulas because they're a bit complicated and involve a whole lot of matrix multiplication stuff. But you have been given these ones, that the beta 1 will be the sxy divided by the sxx. And this sxy is the sum of xi minus x bar, yi minus y bar, and this is sum of xi minus x bar, xi minus x bar. That's the beta 1 hat. And then the beta naught hat is calculated by subbing in beta 1 hat into here and x bar into here. So I get y bar minus beta 1 hat x bar. Yeah. So you have formulas for that in the simplest possible case where there's only one kind of x, but you trust the computer has the formulas in it correctly for the bigger ones. Right. And that's probably all I'll say, other than there are assumptions that go with it. So technically, you do not need any of the assumptions to calculate the line of best fit. That is literally the closest line to your data, no matter how your data is arranged. If your data is not supposed to be a line, it's still the closest line. But in order to do the p-value stuff and the prediction intervals and the confidence intervals, that all has to do, that's why you need the assumptions. There you go. That's enough for today. Thanks, guys.
Are we recording still?
Yeah, we could record this. So, right, you wanted to know about this stuff?
Yep.
Which is the checking of assumptions?
Yes.
Okay. So I might as well write it down because, for the recording.
Catch you later.
Okay, so the idea is in regression that you need various assumptions in order for all your p-values and your confidence intervals to work the way you expect them to work. And so you need, let me see if I remember the assumptions. You need linearity, meaning that it really is supposed to be modelled by a straight line slash plane slash whatever it is.
Yeah.
And you need
Homoscedasticity. Close enough.
Some people spell it with a C in this spot.
That's what I do Hollywood dog.
Yeah. Homoscedasticity, which means that the variance is the same no matter what the x is.
So essentially just a random scatter.
Yeah. And you need normality of the errors, and you need independence between two individuals.
Yeah.
Okay. So, since these are assumptions, you'd want them to be true in order for you to interpret your statistics correctly.
Yes.
And so you need ways of checking it. And so to check the linearity, so let's just, so to check the linearity, so for linearity, you want it that it really is a line, right?
Mm-hmm.
So when you create that line of best fit, you want it to look actually like the points are on either side of it.
Yeah.
And so what you do is you do the residuals versus fitted. Because if it really is a straight line, everything should be down the middle of your data.
Yeah.
And so you remove the line and just have the leftover bit.
Yeah.
So the residuals versus fitted here is supposed to be, I really hope this is actually recording. Oh yeah. Nah, well there's a mic in the bench, it'll just be softer. The residuals versus fitted, we've removed the line and we've got this nice random scatter on both sides of the line.
Yeah.
Okay, so even if it had this funneling effect, it would still be linear
Because it's still a random.
because it's still randomly scattered on both sides of the line.
Yeah.
So you want,
So it's about 0 in that plot, like you want it to.
yeah, random scatter on both sides of 0, of the 0 line. That's what you want.
Yeah.
In this residuals versus fitted plot. Okay. So based on data, do the model assumptions appear reasonable? So we can say in this one, yes, the linearity assumption is reasonable because there is random scatter on both sides of the 0 line in the residual versus fitted plot.
Yeah.
So you say what you conclude, what plot you look for,
Yeah.
and what you saw in order to make the decision.
So linearity is that one there.
Yeah. Okay. Homoscedasticity is, I have no idea what this one's for. I'm sorry, I'm going to have to look them up. But I normally do it from the residuals versus fitted plot as well.
Yeah.
Because what you want is roughly even scatter on either side of the line all the way along.
That's what you're looking more for, the like
Yeah.
funnel kind of.
Yeah.
Yeah.
So you don't want it to funnel down or have a wide on the edges and narrow in the middle.
Yeah.
It's okay for it to be sort of a blob. It's okay for there to be less here than there is here. That's
Yeah.
just to do with there being less data at the edges, not
Yeah.
to do with there being a lower amount of variance. So for homoscedasticity, just let me have a quick look for that word in your lecture notes. Alright, so all of her graphs are the fitted versus the residual versus fitted.
So that
Okay,
one there is our best friend.
That's our best friend. So that's also from the residuals versus fitted. Yep, and what you want is the same amount of spread
So they're
at
quite similar.
all
really.
locations along the line. And what some people do is they cut it into pieces.
Yeah.
So they go, let's cut it into like 4 or 5 bits and go, yeah, there's roughly the same amount of scatter in each bit.
Yeah.
The ones on the edge don't really count as much.
Yeah.
So, okay. And then, let's see, normality of errors. Okay, so this isn't going to tell me about normality, this one, because normality is saying treating all of these errors as part of the same distribution regardless of what x is.
Yeah.
So I have to lump them all together into one distribution and ask myself, is that normal? And that's what the QQ plot is doing.
Yeah.
So you want to do the QQ of the residuals. Yep.
Yep.
And what you want is a straight line. Which it is.
What are the dots and the ends like?
That's just to do with there being less data out here, and so they end up being the normal Q. Because there's less data, that they sort of the QQ plot's marking them as outliers.
Yeah.
They're a little bit lower, a little bit higher, because they're not as far out. They're further out than you expect them to be if it really was a normal distribution, or possibly less far. I can never remember how these things work, but what you don't want is a really extreme S shape.
Yeah.
And you also don't want anything that's not, you don't want something that goes like this.
Yeah.
So I can never remember which way around it goes, but you're comparing what percentage. So as you run along your axes, like your residuals, you're going, well, this is the point where I was up to 2% of my data.
Yeah.
And if I use the mean and standard deviation that I calculated and converted to standard normal, what percentage of the data would I be up to? Like what x should I be up to for that percentage of data? And then you compare the two of them. So anyway. Okay. So that's that one. And then independence cannot be checked. It's from the story. Independence is from the story. And usually is to do with it says it's a random sample.
Yeah.
But otherwise you just have to argue it out.
Yeah. Or you just say
yeah. So I'm not sure if you've been taught to use these plots.
I feel like she loosely sort of went over it, but I kind of look at them and I'm like, what does this mean?
Scale location plot.
I know I lost a couple of marks in assignments because I didn't comment on them, but I was like, I don't know what they mean.
It says here that the scale location plot is used for constant variance.
I think she said the residual versus leverage one isn't too important.
Well, it wasn't in the it wasn't. If you look at this, linearity is residual versus fitted, and scale location was for constant variance.
Yeah.
But I can't see what she's looking for. Seriously? Well, Google is our friend. Come on. For future reference, don't use Horace Lamb anymore. It's just so close to the Maths Learning Centre. Sorry? Yeah, I know, but people get annoyed if I use the really, really big ones. Anyway. But maybe that's why no one uses Horace Lamb, because it's dodgy. Scale location plot for, what was it, homoscedasticity? There we go.
I think it was something to do with you wanting to see a like straight line across the...
We're just seeing if there's a pattern, so we just want random scatter. Okay, so the other option, just to add to the pile, is also, yes indeed. Homoscedasticity is from the scale location plot. And what you want is random scatter. That's what it says you want. So I would suggest that in this course, just see below, right? Alright, so that you are allowed to use this if you don't get given one.
Yeah.
If you were only given these two, then you would use that for the homoscedasticity.
Yeah.
But if you have a scale location plot, then you want to use that for homoscedasticity.
Yeah.
That's my instinct for what your lecturer would be expecting you to do. Normality,
and
homoscedasticity.
and then independence. Is
I
just
think the
from-
residuals versus leverage is helping you to find outliers.
Okay.
But they didn't talk about that. So,
Cool.
yeah, and it looks like random scatter. I have no idea what this would look like if it wasn't homoscedastic, but I presume there'd be some sort of pattern.
Maybe
it
the
would go
line
like
in the middle would.
yeah, I think this line's saying that there's a very slight bump like that.
Yeah. So I guess if it was more.
If it was less flat.
Yeah.
Yeah. All right.
Cool.
There you go.
Awesome. Much appreciated.